All right, so for this problem here, we do have two graphs. So this kind of is a continuation of what we were doing last time, but I'm just including it in the second video for this homework. So we have two graphs here. One we see is distance on the x-axis, the other is time. And we want to determine the same five quantities we've been determining: velocity, frequency, period, wavelength, and amplitude. And so I'm going to start out by getting whatever information I can from the graph. So first of all, I see that in both cases, the peak is up here at a maximum value of 40 meters, and that will be my amplitude. So I can say that my amplitude is going to be 40 meters. The other thing that I can get is I can go ahead and determine both the wavelength and the period here. So the wavelength is the distance for one full wave. So I see that the wave begins repeating itself right there, which means that one wavelength is going to be 4 meters, this entire distance here. And the period, I see the period begins repeating itself here, so one period will be that interval of time there, which is 0.4 seconds. From there, I can do a little bit of math and determine the other two quantities. So first I can say that frequency is just 1 divided by the period. So my frequency is going to be 1 over 0.4, which gives me a frequency here of 2.5 hertz. And then now that I have that frequency combined with the wavelength, I can go ahead and solve for my velocity, which is just wavelength times frequency. So that velocity is going to be 4 multiplied by 2.5, which gives me a velocity of 10 meters per second. And so there I have that. All right, so moving on to this next one, we have a few different wave phenomenon described, and we want to say which one of these four words matches the description and gives the wave property demonstrated by the description. So the first one, sound waves hit mountains and bounce back. And that's really the key idea there. They're hitting and bouncing back, creating a good echo, and that is an example of reflection. So that first one is going to be reflection. When a sound wave hits a sandbar, the depth of the water decreases, the wave changes direction, and the key idea there is changing direction or bending, and that is an example of refraction. Waves spread out when traveling through a narrow opening in a bay. Waves spreading out, that's the key idea there, and that's an example of diffraction. When two waves collide, it makes an even bigger wave. So waves combining to make a bigger wave, that would be an example of superposition. Specifically, that would be destructive or constructive interference, but superposition by itself is enough. Sound waves travel better over water because the cold air bends, all right? Air bending or changing directions, that is going to be an example of refraction, once again. Soprano and baritone sing at the same time, and it produces a more complex wave. So these two waves together from each person, making a more complex wave, that is another example of superposition. And lastly, it's difficult to hear in a gym because the sound waves bounce off the walls. That idea of bouncing off the walls, that once again results from reflection of sound waves similar to an echo. So that last one is going to be reflection. Moving on to this next one, these are just some conceptual questions about sound waves. So someone tells you to turn that music down because it's too loud. What do you need to change about the sound wave to do this? And that really is a function of the amplitude. So amplitude is what affects the volume of a sound wave. More amplitude means more volume. All right, so you're told here that your pitch is off, and we want to know what we need to change about the sound wave in order to correct that. Pitch is really a function of frequency. That's what affects the pitch of a sound wave, and so the frequency in this case must change. All right, so for this next one here, we once again have two graphs. These are now graphs of sound waves, and we do see that the y-axis here is measured in pascals, units of pressure, because sound waves are simply just pressure waves. And the first thing we want to do is calculate the frequency of both waves. So in order to do that, I'm going to look and see that that x-axis is in time, meaning it will give me my period. And so I'm going to look for when these waves start to repeat themselves. So for this first wave, I see that right there it starts to repeat itself. That time, that interval, is going to be 0.025 seconds. Okay, and so I can go ahead and calculate my frequency based off of that. Frequency is 1 over the period. So the frequency is going to be 1 over 0.025, which gives me a frequency here of 40 hertz. So that would be the frequency of sound wave A. Okay, moving on to sound wave B, I'm going to look once again for when it starts to repeat itself, and I realize this is a slightly more complex wave. It's not a simple sine curve, and we'll talk a little bit more about that as we move on, but you still can look for when this wave starts to repeat itself, and that occurs at this point right here. If we look then after that point, the wave starts over, and so our period would be this interval of time here, which means that for that second wave, the period is going to be 0.02 seconds. And so my frequency, still 1 over my period, would just be 1 over 0.02, which means my frequency here would be 50 hertz. Question B here asks which wave has a higher pitch. And so pitch is related to frequency, so we're going to say B, and our reasoning is because it has a higher frequency. And then finally for C, which wave is louder? Loudness is related to amplitude, so we're going to look here and we see that wave B has an amplitude of about 1 Pascal here. Whereas the other wave has an amplitude in between 0.4 and 0.6, so about 0.5, which means that wave B is going to have a greater amplitude, and therefore it's going to be louder.